So since the beginning of the electrical age, we have been trying to figure out ways of encoding the written word using electricity. And this effort started in the late 19th century, and then in the early 20th century, given some of the examples in the slides here. To try to provide some standard way of exchanging this electrical information as computers started to come onto the scene, the American standards, the United States created an American Standard Code for Information Exchange, or ASCII. And this emerged in 1963. So ASCII is actually quite old. It's even older than I am. And ASCII was designed really just to represent characters and symbols that were used in American English. But you know, computers were not just in the United States. And so other countries wanted to also use computers, but had letters that were not represented in ASCII. So there were a number of other national standards emerged that included characters, say, with the accents over them. So there's an example here where there are the ASCII characters on the top line, one of the national standards, and then what the representative byte code is, or what the representative ASCII code is. So for example, the first column, an open curly brace, is in US ASCII is 123, but in one of the national standards, it represented the A with the 2 dots over it. This also then led to, in ANSI-C, the introduction of these trigraphs, because of course open curly brace is needed for C programmers, but if you were using that national standard, that wasn't one of the characters available to you. So there had to be some accommodation for this problem. Then in 1987, in sort of an effort to consolidate or standardize a lot of these national standards on a more international basis, a new standard emerged in 1987 called Latin 1, which goes by some other names, which are listed there. And here, Latin 1 takes advantage of the eighth bit. ASCII was a 7-bit standard, so there were only 127 usable characters in ASCII. So Latin 1 said, hey, why don't we use that extra bit, which ASCII was using as a parity bit, to encode more characters. So now we've, instead of 127 possible characters, we get 256 possible characters. So Latin 1 covers 191 characters from mostly Western European languages. There were other parts to Latin 1. It has 15 different parts, which kind of like the national standards covered other European languages and Asian languages. So for example, it covered Cyrillic and the Greek letters and some Asian languages, which I don't remember. But this standard still did not have any provisions for what are referred to as the CKJ, Chinese, Korean, and Japanese languages, right? Where there are pictograms, so there's more than 256 characters. There are thousands of characters. So Latin 1 doesn't accommodate CKJ at all. But it did expand the number of a number of countries that could use the same kind of character set encoding. So here's another example where, say, in Sweden, right, you want to say sandwiches, and in the byte code for those characters, right, is, say, for example, the closed brace, right? In American ASCII, it's a closed brace. It's the character 125. But in the Swedish National Standard, that was the A with the circle over it. But for Latin 1, it now had its own character encoding. It was number 229. So now, if a programmer were using Latin 1, in Sweden, they would still be able to say sandwiches and also be able to program with a closed curly, right? So it really simplified things as far as it being an international language. But this standard, Latin 1, is still 1 byte per character. It also required that all programs become 8-bit clean. If you're old enough to remember programming before Latin 1, a lot of programs were not, that only dealt with ASCII characters, were not 8-bit clean. They assumed that ASCII, that a string was only 7 bits worth, and often used the 8th bit to mark certain things, like maybe the end of a string or something, right? So there was actually a significant effort in the up through around 2000 to try to make a lot of programs 8-bit clean. All right, but like I said, this still doesn't help. Doesn't help for the Asian languages. So of course, there were computers in Japan, China, and Korea. And so there was a variety of emerging standards for how to encode those languages, the characters in those languages, into bytes. And there was basically this explosion of different standards, which were very difficult to manage. So in '91, a group, I think at UC Berkeley, started formulating this idea of Unicode, where a Unicode is a 24-bit system. So there are 24 bits to represent each character. And this would allow for over 1 million code points. So you could encode over 1 million different kinds of characters in Unicode. And so the initial standards covered basically 150 different modern and historic scripts, lots of symbols, lots of emojis. But it is a 3-byte standard, right? So every character needs 3 bytes to be represented. So what does that mean? Okay, so in Erlang, we can use a list to represent a string. So instead of, when we usually think of doing this in, say, Latin 1 or English, we have the ASCII codes or the Latin 1 codes as each of the elements in the list, like in the first example. So the Erlang makes this very easy to think about, because it's, well, now they're, instead of just being ASCII or 1-byte characters, now we can think of them as Unicode code points or 24-bit values. So instead of it being restricted from 0 to 255, now we can say, wow, we can make these much bigger numbers. So we can easily represent Russian or Arabic, Greek, Chinese, and emojis. So one of the interesting things to notice about this pattern, about these values, is that in general, sort of the living languages will have code points that are at the smaller end, the lower end of the 24 bits, and characters which are more, maybe not as commonly used or more frivolous in a sense, tend to be at the higher end. So you'll notice that things like the emojis have very large values. So they're kind of towards the end of this 24-bit range. And there is this sort of Western bias to it, because the Latin 1 characters, the characters coming from Latin 1 all tend to be single-byte characters. Okay. All right. So now we have a list of the characters, but we need some way of representing that list as a string of bytes, right? So, because if we have a series of, say, of emojis, how do we want to go back one slide here? How do we want to represent those 3 large integers as bytes in order to exchange this information with some other program? So what emerged were standards called UTF 8, 16, and 32, which are ways of taking the Unicode code points, the integers, and turning them into bytes that can be exchanged between programs. So the simplest way of doing this would be to use a 32-bit value for each of the characters, right? So that's UTF-32. So we just use 4 bytes for every character. But then we have to know if it's a big Endian or a little Endian value. The second way would be to use something called UTF-16, where we chunk it up into 2-byte values. But 2 bytes, remember, isn't large enough to store a 24-bit character code point. So the encoding scheme has a way of saying, well, if it's smaller than a certain value, then we can put it in 2 bytes. But then if it's bigger than that, then we're going to use 4 bytes, right? So this takes advantage of the fact that most of the commonly used characters are at the lower end of the value range. So most of the characters could get stored in only 2 bytes, but then for the more exotic characters, then we start using 4. And then similarly, we can extend that idea one step further with UTF-8 and say use 1, 2, 3, or 4 bytes to represent a character. So now if you're an ASCII character, those are all going to only use 1 byte. But if you are moving up the range, say to the Latin 1 characters, then maybe it's 2 bytes. And we can see that in the next slide. Here we go. So looking at the example here of sandwiches, smorgasbord again, you can see that the Unicode code points, which are all relatively small numbers, and then the code point for the emoticon, the smiley, okay, which is a very large number. So in UTF-16, we would represent the values as a 4-byte integer in binary, and that's pretty straightforward. And for UTF-16, for the letters, it's also pretty straightforward. But then for the emoticon, you can see that there is some kind of encoding that is happening so that something trying to decode the bytes knows that, oh, this is a 4-byte value, not a 2-byte value, right? So that's why that that first byte has a different value. UTF-8 gets interesting also, because you'll notice that for the 2 accented characters, now they are taking 2 bytes instead of 1 byte like for the others. Like the S is 115, but the O with the 2 dots over it is 195, 182. So the 195 is telling the code that is decoding the bytes that, hey, this is a 2-byte value, and then the 182 is part of that value. Okay. And then finally, the same thing in Latin 1, which remember was the 8-bit standard, right? The unaccented letters are the same. The accented letters are in the with the 8-bit value, the high bit set to 1, so they're all over 128. But they don't match the UTF-8 value, right? So in so non-ASCII Latin 1 characters need 2 bytes in UTF-8, but ASCII Latin 1 characters are still represented as 1 byte. So what you can get from this is that UTF-8 is compatible with the ASCII characters from Latin 1, compatible in the sense of the values are the same, but it is different for the non-ASCII Latin 1 characters, right? And there is often confusion over that, where people will say, well, Latin 1 and UTF-8 are the same, and in fact, they're different. Okay. Oh, and then finally, the emoticon in Latin 1 gets mapped to character 26, which is the character which I believe is a control character that says that there is no encoding. And that's often displayed as a box, an empty box, or a diamond with a question mark in it or something like that, to indicate that there was a character here, but it had no encoding in the character set encoding. All right. So what does this mean in Erlang? What are some of the things that we need to change in our Erlang code to start using Unicode character strings? So the couple of the obvious things that need to change are in format strings, adding the T option, which tells the formatter, the ~s formatter, that the string might have Unicode Unicode characters in it. And for the regex or the RE module, adding the Unicode option so that it will treat the characters as Unicode options. And then something that can also be very helpful is to add the +PC Unicode option to URL, which changes the heuristic for deciding if a list is a character string. So in if you when you have a list and the shell prints it, sometimes it comes out as a list of numbers and sometimes it comes out as a string. And there's a heuristic that the shell is using to decide which way to show a string, or which way to show a list. And so adding the +PC Unicode changes that heuristic so that it will treat lists that look like a list of Unicode characters as a string instead of a list of integers. So this can be pretty helpful if you're doing a lot of work in Unicode. And then for conversions between lists and byte strings, the Unicode module is the place where all of these things are. So the two, I think probably commonly used or probably for this purposes of this presentation was useful functions are characters to list, which will take a list of characters, so basically like an IO list, and then encode it into, decode it. All right, try again. So characters to list will take a list of an IO list or a binary and decode it using the provided encoding value. So in this case, we are taking the 4 bytes, treating it as if it is a UTF encoded string, and decoding it into the bytes. Into the characters. So we end up with the 4 bytes, which turn into the 2 characters, the O with the 2 dots and the A with the circle over it, right, from the previous slide. So just be clear. So characters to list is doing the decoding. So it is taking a binary that is in some kind of UTF encoding and turning it into the Unicode code points as a list, right? The reverse is characters to binary, which is going to take a IO list and encode it into the bytes in the format that's requested. So you can so in that way you can generate a UTF-8 encoded string from the Unicode code points. Then it also has the option of doing sort of transcoding. So if the input is UTF-8, but you want to output UTF-16, it can do that for you, right? So that's the in encoding. So the in encoding is what is the encoding of the subject string, and the out encoding is how should the resulting binary be encoded. Okay. All right, so how does this apply to what we do at Datometry? So this is a very high level architectural diagram of the Datometry Hypercube product. And basically it's a really, one way to think about it is that it's a very large, complicated gateway between one kind of database engine and another. So as an example, on the left side, there could be applications using native DB libraries from Teradata. So the left-hand side is talking the Teradata network protocol and talking to us, thinking that Hypercube is Teradata. We then ingest the SQL or the data or what have you, translate it into the SQL and network protocol that's needed by one of the data warehouses on the cloud, like Redshift or Azure Synapse. And then when the database engine, the cloud database responds, then we need to take those responses and translate them back into the network protocol of Teradata. So it's basically like a big complicated gateway. So in order to, oh, and then, so Teradata made, the Teradata protocol is a little challenging in that it allows the client to specify the character set encoding. So it can say, oh, I'm going to talk Latin 1, or I'm going to talk UTF-8 or UTF-16. And so we had to be able to, when we extracted the strings and dealt with the protocol, we had to be able to translate those into the character set encoding that we wanted to use talking to the cloud service. So what are the changes that we had to make? So we had to remember the client's preferred encoding. We had to make sure that we were setting the encoding correctly on the cloud side. We changed all the format strings. We had to find all the places we use the RE module and add the Unicode option. Then there were the things that were a little more subtle. For example, we could no longer use byte size to figure out how many characters there were in a binary, because there's now, using UTF-8 encoding or any of the encodings breaks the assumption that there is 1 byte per character. Similarly, we couldn't use list to binary or binary to list to translate a list of Unicode code points into a binary, or take a binary, say, off the network and turn it into a list of characters, because these things are now needed to be encoded and decoded correctly. So instead of using those, we had to find all the places that we're using these and change them appropriately, because sometimes they did want to be binary to list, into Unicode characters to binary and Unicode characters to list. This was probably one of the more challenging things, was finding all the places where there were these sort of quiet switches between binaries and lists. So some examples, using IO format, changing the IO format, changing all the REs, calls to RE, changing how we interpret binary values coming off the network. This was, this was all pretty confusing and complicated. So a couple of the things that we did to try to keep our sanity was that we decided to standardize on certain things. So we decided that within our, between the two networking ends, so between the reading the data from the client and writing it out to the, reading the data from the Teradata client and writing the data out to the cloud database, that within that range of code, everything would either, strings that were as lists would always be as a list of Unicode code points, and any binaries would be UTF-8 encoded. So if it came in a different format, we would switch it to that. And if we needed to talk to the cloud database in a different format, then we would change it right at the network, at the point that we were sending it over the network. This helped simplify things incredibly, so we didn't have to remember all the way through the code what the encoding should be. We also tried to make sure that we tested did all our testing with data that we could actually read, because if you use things like Chinese characters or use Arabic, the Farsi, if you can't read it, you don't necessarily always see the subtle differences. So it was important that we tested this with characters that we could actually read and distinguish, and also to use a variety of strings, since the encoding is very data dependent. Having a variety of input data helps track down bugs. So the confusion around character set encoding, I think, comes from a few places. One is that the vendors that are writing documentation also seem to get confused about what they're talking about and use the terminology in the wrong way. And then for things like Teradata, even their terminology was kind of confused. And in fact, they have these other restrictions like UTF-8. Something that was UTF-8 encoded could really only be up to 3 bytes, and UTF-16 could only have 2 bytes. So that was not even quite the standard. and in say like Microsoft documentation, Unicode sometimes meant just 16-bit characters, but not all of Unicode. So I think that the vendors also contribute to the confusion by not being very clear themselves. Okay, wait a minute, trying to go to the next slide. Oh, there we go. Okay, so some of the problems that we ran into were that even though the results looked right, there was actually still something wrong. And the problem can come from the look at what's happening at the two ends. Everything kind of, or looking at one end, everything kind of looks okay, right? Um, so so this is something that we had to look at carefully and spent a lot of time actually doing debugging on. The other thing is that we had a lot of confusion within our own team about what Latin 1 meant versus UTF-8, and had to make very clear that UTF-8 is, Latin 1 is not compatible with UTF-8, only ASCII is. And for our system, all the spots in red represent places where encoding could happen. So the application could encode the data before it gets sent to the drivers. The drivers could encode the data depending on the connection string setting. When we send the data back out, we're encoding it to talk to the ODBC driver of the cloud database. The ODBC driver itself can be configured to do encoding, and then it ends up in the cloud database, which may do some encoding again on its own. And then the whole thing is reversed when you pull the data back out. So it's very easy for there to be mistakes or double encodings along the way, which were very hard to track down. Because if you're doing all of your testing sort of at the client side, then, oh, I put some data in, looks the same, I'm done, right? But in fact, the data that actually gets written into the database could be wrong. So some of the key takeaways for us was, some of the key takeaways from this presentation would be that to remember that when we talk about a character set, we're talking about a numeric value that represents a character. When we say encoding, we're talking about serializing those characters into bytes using some strategy like UTF-8. Unicode is a character set, right, that code points for all characters. We need to not think about one byte as being one character. We also have to remember that UTF-8 is compatible with ASCII, the ASCII portion of Latin 1, but not the non-ASCII characters, right? So basically accented characters. We also found that encoding and decoding needed to happen in all sorts of places. And so it was very important for us to look at the particular bytes at different stages, look at the number of bytes, and then look at the character lengths, and making sure that everything was matched our expectations. And then the other thing that causes a lot of confusion was that if you were cutting and pasting values, maybe the terminal is also doing some character set encoding for you, or the app that you're using, like Data Workbench or something, might also be doing some encoding or decoding. So you could end up with not seeing the right bytes. So looking at the actual bytes turned out to be pretty important. And just the example there, if double encoding is the same, gives you this, double encoding and double decoding looks right, but when you're at the equal sign, the values are not the right thing. So that's it. I hope this was useful. There's just a little bit of information there about tautology, and I think we've got a few minutes for questions.